All right, so we're going to look at categories of nomenclature here, okay? In this class, at this point in time, we have 4 categories. All right, we've got molecular compounds that are non-organic. These are covalent compounds. So molecular, non-organic, and molecular means it is covalent. That is to say, there are sharing of electrons. Then we have the category of ionic compounds. Okay? Then we have the category of non-organic acids. And then we have the category of organic compounds. And these are also covalent. Now, there were a few network covalent structures that we looked at on a video, okay? But those are kind of a separate thing, all right? You kind of need to know what a network covalent structure means and what an allotrope is, okay? But that's kind of a separate category from nomenclature. All right. Organic covalent. All right, so then if we're going to go through these by category, all right, so molecular, non-organic. If we're going to have a formula and write a name from the formula, here's a formula, and the way that we write the name from the formula is we simply use prefixes to indicate the number of elements or atoms in the formula. I've got 2 nitrogens. That would be a dinitrogen. Dinitrogen. And 5 means there are 5 oxygens, and it's oxide. So the end of the word is going to be changed. The second word is always changed to IDE. Dinitrogen pentaoxide. Now the A is supposed to be dropped here, okay? Whenever you have A before some other vowel, okay, then that A gets dropped, so it should be pentoxide here, okay? If it were pentachloride, it would be pentachloride, but oxide, you drop that A off that, so it's just pentoxide. That's all one word here, okay? All right, so if we have a name of a compound, like sulfur dichloride, then you're just going to write the formula from that name. There's 1 sulfur because there's no prefix indicating anything else. Dichloride means there are 2 chlorines. All right, ionic compounds. When we're naming ionic compounds, there are a couple of different categories, at least the way that I categorize them. One of them is that we have just metal and non-metal combinations. But even with the metal non-metal combinations, there are 2 different things you have to remember. If the metal has only one kind of oxidation number, so let's use this as an example. This first column of elements all have a 1+ charge and no other kind of charge. This second column of elements all have a 2+ charge and no other kind of charge. Same with the third column. This column right here and this column right here. All the metals in those columns only have one kind of charge. So when you put a metal with a non-metal from one of those columns, those metals don't need a Roman numeral to name them. Okay? So if I'm going to use scandium and say chlorine, to name that, I don't need a Roman numeral to name it. This is simply scandium chloride.
What does ion mean? A non-metal metal? Question probably already been asked, but I just...
Now, if I have a compound that's made of a metal that has more than one oxidation number, let's use vanadium as our example here. It has 4 different oxidation numbers. I can still have virtually the same formula, but it's not enough to call this vanadium chloride because there's 4 different ways you can combine vanadium and chlorine. So I need to say which charge this vanadium has. Okay? So looking here, I can see I've got a 5+, 4+, 3+, or 2+ option. The way I figure out which charge this one has is to figure out the charge on the nonmetal. So vanadium, we don't know the charge for. Chlorine, we can figure out the charge for. While vanadium has 4 different oxidation numbers, they're all positive. So the charge on the chlorine has to be negative so that I can have a neutral compound when I'm done. So chlorine has only 1 negative charge, and that's a 1 negative. So if this is 1 negative, and if I have 3 of these chlorines, that's 3 negative charges. So that if I only have 1 vanadium, the only way to get a neutral charge, a 0 charge, is if the vanadium has a 3+ charge. Okay? That means that this compound then is known as vanadium 3 chloride. Vanadium Roman numeral 3 because of the 3+ charge.
You only put the Roman numeral if it's an ionic compound?
Ions. Then there are ionic compounds that also contain ionic compounds. I'm sorry, polyatomic ions. Let's see. We didn't actually write a formula from a name yet, did we? Let's do a formula from a name first, then we'll go to the other, okay? So let's see. How about we do... All right, calcium oxide. To find out how to write the correct formula, I need to figure out the charges on the calcium and the oxygen. Calcium has this symbol, and all the elements in column number 2 have a 2+ charge. Oxygen has a number of different possible charge numbers, but unless you're given some prefix or something else in the name to tell you there's a different charge, you're always to assume oxygen has a 2 negative charge.
Well, you just assume that?
Yes. Unless there's a PER in front of the oxide, then you don't assume there's any other charge. Okay? All right. Most of the time, oxygen is going to have a 2 negative charge. All right. So that's already balanced out. We just need 1 of each of these.
You need what?
1 of each of these. 1 calcium, 1 oxygen is balanced. So the formula for calcium oxide is Ca capital O. Okay?
That's calcium oxide.
Manganese 7 oxide. Alright, so manganese 7 means that I have a 7+ charge on the manganese. Manganese, by the way, there's a word or an element that sounds very close to this. That's magnesium. This is not magnesium, this is manganese. Make sure you look for the right symbol. This is M sub N, and it's going to have a 7+ charge on it. Okay? What did we just say about the charge on the oxygen? Always 2 negative unless there's something else to show you otherwise. Not 2 positive, 2 negative. Okay?
You said 2 positive.
I just said I wrote down the wrong thing. All right. So now, what ratio of manganese 7 and oxygen do I need to give me a balanced compound? What coefficients could I put in front of this and in front of this?
2 and a 5.
A 2 and a 5. Very good. That's perfectly right. Okay. So a 2 here will give me a total of 14 positive charges, not a 5, a 7 here. And a 7 here will give me a 14 negative charge. Okay? So when we write the formula for this then, we need a subscript 2 behind the manganese and a subscript 7 behind the oxygen. 14 positive charges, 14 negative charges. It's a neutral compound.
You just lost me at that 7.
All right. Let's give you a formula here with a polyatomic ion.
What's that, Mike? Hey, slide it up, please. Upstairs a little louder. You say what?
All right. So manganese has more than one oxidation number. We just said that. So we don't yet know what its oxidation number is going to be for this compound. It might be 7, or it might be any of the other 4 possible oxidation numbers. We're naming it. Now, when we have more than 2 elements, there's probably a polyatomic ion in here. So we're going to go to the periodic or the common ions list and find some part of this formula that has a polyatomic ion in it, and that's sulfate. SO4. SO sub 4 is sulfate. Okay? And that has a 2 negative charge. Okay, so we know that sulfate has a 2 negative charge. We can look at this formula and we see that we have 2 manganese ions of some kind, and we have 3 sulfate ions. Now from this math then we should be able to figure out what charge is going to go here. This is 3 times 2 negative, that's 6 negative charges on this side. 2 times something has got to be a 6 positive to balance that out. Okay, so that's got to be a 3 positive charge on the manganese. So the name of this ion then is manganese 3. Okay? There are 2 categories of acids. All right, there are the non-organic acids. There are 2 categories. There's binary, and there's those that contain oxygen, or those that have polyatomic ions. With binary acids like this, because there's 2 elements and only 2 elements. Elements. Hydrogen and chlorine are the only 2 elements in this. That's two elements. That's binary. So this is going to be named first like an ionic compound. You first name it like it's hydrogen chloride. That would be naming it like an ionic compound. Okay? To name it like an acid, we're going to drop the gen off of hydro and make hydro a prefix on the chloride. We're going to change the ID ending to IC, and we're going to put the word acid on the end. Hydrochloric acid, yes. say I give you I'm going to give you hydrosulfuric acid. That hydro prefix here is your clue that this is a binary acid. It's only going to have two elements. No more than two elements. One of those elements has to be hydrogen. Okay, because acids, non-organic acids, always have hydrogen in them. In fact, most acids do. Sulfuric, if it's binary, means it's only a sulfur ion, not a sulfate or a sulfide ion. The hydro tells us it's only two elements here. It's a binary acid. So we've got to have an S, and we've got to figure out the charge that goes on the sulfur. And you look that up on the periodic table here. You see that the elements where sulfur is in this column, where everything is 2 negative in a binary compound. You can double check that and see over here that sulfur has 4 different oxidation numbers, but only one of them is negative. Since hydrogen is positive, sulfur has to be negative. So this is 2 negative, and to balance that out, I need 2 hydrogens. So this formula for this acid is H2S. Now, if we have an acid that contains a polyatomic ion, it has a little bit different naming system. Okay, so if we have a formula like HBRO, we have more than 2 elements here, and some of those aren't carbons. So we're going to look and see if we can find this. No, this is still well, it makes it the polyatomic ion acid, or the oxy acid. Yeah. Okay. So we're going to look and see we have more than 2 elements. And we're going to look for some part of this formula that's on our common ions list. And BRO is hypobromite. Okay? So if we name this like an ionic compound, that's what you always do with acids. You name it first like an ionic compound. It would be hydrogen hypo, not hydro, but hypobromite. Okay?
Bless you. Bless you.
Now, when you have a polyatomic ion in the acid formula, you drop hydrogen entirely. You change I to OUS, and you put the word acid on the end. So this is hypobromous acid. So if I give you a name like nitric acid, okay, there's no hydro prefix. So since there's no hydro prefix, this must have a polyatomic ion in it. We're going to look for NITR, and since I have an IC ending, I'm looking for an ATE ending. Okay, so what I'm looking for is a polyatomic ion called nitrate. Okay, ite endings become us, ic endings become ates, or ates become ic endings. Okay,
Because it's a
hypo, because this is hypobromous or hypobromite, the hypobromite ion. So we're going to look for a nitrate ion, NO3 negative. I'm looking for enough hydrogens to balance that out. I only need 1. So the formula for nitric acid is HNO3. Okay? Now, with organic compounds, you have to memorize the prefixes up to 10 and the suffixes for single, double, and triple bonds and side chains. So the prefixes for 1 to 10 are meth, eth, prop, but, pent, hex, hept, oct, non. The suffixes for a single bond when the main chain has nothing but single bonds is ane, ane. The suffix for a double bond in the main chain is ene, and the suffix for a triple bond in the main chain is ein. The suffix for a side chain is yl, ill. Okay? So if I have a carbon chain, 1, 2, 3, 4, 5 carbons long, there's no double bonds, there are no triple bonds, so this must be 1, meth, eth, pro, but, pent, hex. This is hexane. Alright, so then if we have a name like pent 3-ene, we can figure out the shape of the molecule or the structure of the molecule. Pent means the main chain has 5 carbons in it. 1, 2, 1 on each end of that line, 2, 3, 4, 5. And I have a double bond on number 3. 1, 2, 3. Oops, guess what? That's pent 2-ene because we should be numbering from the right. Now, these are skeletal structural drawings. You have to also be able to do complete structural drawings and condensed structural drawings.